In this last video of this lesson, we show a method of reconstructing an actual solution from two tables computed by our dynamic programming algorithm. Okay, here on the slide we see two tables M and capital M computed by our dynamic programming algorithm, which contain minimal and maximal values respectively for all possible sub-expressions of our initial expression. Let me first put the indices for all the rows and columns of these two matrices, as well as numbers for our initial digits. Well, in particular, we see by reading the contents of this cell, capital M of 16, that the maximal value of our initial expression is equal to 200. And our goal is to unwind the whole solution, parenthesizing of the initial expression from these two tables. So our first goal on this way is to understand from which two sub-expressions of the initial expression the value 200 was computed. Well, let's see. When computing the value for the maximal value for sub-expression 16, we tried all possible splittings of the expression 16 into two sub-expressions. Well, let's just go through all of them. The first possibility is to split it into two sub-expressions, 1, which corresponds just to the first digit, which is just 5, and sub-expression 6 with a minus sign between them, right? So for both these two sub-expressions, we already know minimal values and maximal values. Well, let me mark them. So this is the minimal value for the sub-expression 1, this is the maximal value for sub-expression 1. For 6, this is the minimal value, minus 195, and this is the maximal value, 75. So we would like to maximize this sub-expression 1 minus sub-expression 2, which means that we would like the first sub-expression to be as large as possible and the second sub-expression to be as small as possible. Well, this means that we need to try to take the maximal value of the first sub-expression, which is 5, and the minimal value of the second sub-expression, which is minus 195. Well, we see that in this case 5 minus 195 is the same as 5 plus 195, which equals exactly to 200, right? Which allows us to conclude actually that the value 200 can be obtained just by as follows. So we subtract the minimum value, which is minus 195 of the second sub-expression from 5, right? So we restored the last operation in an optimal parenthesizing of the initial expression. However, we still need to find out how to obtain minus 195 out of the second sub-expression. Well, let's do this. Okay, so we need to find the minimum, how the minimum value of the sub-expression 6 was obtained. Well, there are several possible splittings, once again, of the sub-expression 6 into two smaller sub-expressions. The first of them is to split 6 into 2, which just corresponds to the digit 8 plus 36. Well, in this case, we would like the value to be as small as possible, and our sign is plus in this case, which means that we would like the value of sub-expression 2 to be as small as possible, and the value of sub-expression 6 also to be as small as possible. And we already know these values, they are in our tables. So the minimal value of sub-expression 2 is 8, while the minimum value of sub-expression 6 is minus 91. right? So we see that the sum of these two values is not equal to minus 195, right? Which means that plus is not the last operation in the optimal parenthesizing that gives the minimum value of sub-expression 2,6. Right, so let's check the next one. Another possibility to split the sub-expression 2,6 is the following. We split it into sub-expression 2,3 times sub-expression 4,6. Right? So once again, we would like to find the minimum value of sub-expression 2,6. Well, let's see just all possibilities. The minimum value of sub-expression 2,3 is 15. Its maximal value is also 15. As to sub-expression 4,6, its minimum value is minus 13. Its maximal value is 5. And we would like the product of these two values to be as small as possible. Well, it is not difficult to see that if we take just 15 and multiply it, which is the minimum value of sub-expression 2,3, and multiply it by the minimum value of the sub-expression 4,6, which is minus 13, then we get exactly minus 195. And this in turn allows us to conclude that to get minus 195 from the sub-expression 2,6, we can do as follows. We can first compute the sum of 8 and 7. This gives us 15, and then to multiply it by the result of the second sub-expression. Well, now it remains to find out how to get minus 13 out of this sub-expression 4,6, but in this small example, it is already easy to get minus 13. Well, we just first compute the sum of 8 and 9, and then subtract it from 4, right? So this way, we reconstructed the whole solution. I mean, an optimal parenthesizing or an optimal ordering of our arithmetic operations, leading to this value, to this maximal value 200. Let's just check it once again, that our parenthesizing leads to the value 200 indeed. So we first compute the sum of 8 and 9. This gives us 17. We then subtract 17 from 4, and this gives us minus 13. We then compute the sum of 8 and 7. This gives us 15. We multiply 15 by minus 13, it gives us minus 195, and finally we subtract this number from 5 and we get 200 indeed. So we reconstructed the whole solution. In general, I mean, for an expression consisting of n digits and n minus 1 operations, the corresponding algorithm makes roughly quadratic number of steps, because it needs to reconstruct n minus 1 operations, I mean an order of n minus 1 operations, going from last one to the first one, and for each operation it potentially needs to go through all possible splittings into two sub-expressions, and this number is at most n. So the running time is big O of n times n, which is big O of n squared. And this technique is quite general. It applies in many cases in the dynamic programming algorithms.